Otto versus Diesel versus Brayton, and all of these compared with Carnot. Okay, so we'll get a as we do this, we'll get a feel of also a few other things which will be useful over the next few lectures. And let me draw TS diagram. Let's say this is the Otto cycle. And we will draw the limits of the maximum and minimum temperatures. The maximum and minimum temperatures, as we had said earlier, is defines they have physical meaning. That's why we are putting it. Minimum temperature being the ambient temperature, maximum temperature being the temperature of the fuel burning. You know, those are the kind of things we want to, or the maximum temperature is where we want to reach, what is limited by the material properties, or the properties of the material of the turbine blades or the combustion casing, whatever material we have in an engine. Okay, I had drawn, so this is Otto cycle, which is V equal to constant combustion, we said, and well, we replace combustion with an heat addition, equivalent heat addition at that constant volume. When you go to a diesel cycle, that is the only step that changes, and we say it is a constant pressure, and we had drawn a line like this. Now, why do we draw a line, a constant pressure line, lower than a constant volume line? Anybody has figured it out already? Let's, we need to, okay, one way to approach it is, can we say that the slope at this point, at point 2, where both the lines are starting, can we say that one of them has a higher slope than the other? That would give us a reason to make one higher. So then what would be the slope of any of these lines, and how would we get it? PV to the power gamma. Okay, so and then we'll get T and V connected, and then, so it's a TS plot, remember that. The slope, what's the slope on TS plot? Yeah, dt over ds equal to the slope. The idea is very simple, it's just geometry, but you know, these are things that will help you to understand the mechanism of the engine very shortly and its components, a compressor, a turbine, all those things will come up. And how do we get this? Is it an equation which relates these two? The so-called Gibbs equation. TdS equal to dH, which is Cp dt. Remember, we are working with ideal gas now. Minus dP by rho, right? Please check. So here you go. For the constant pressure process, it's fairly straightforward. What's the slope for constant pressure? Yeah? T by Cp. Everybody agrees to this? Constant pressure, dP is 0. And what about the constant volume? Can somebody just think a little one step further and come up with the answer? it's almost obvious. It's almost, it can be easily extended, but if you can do it with the equation, that's better. Cp by Cv. Replace Cp by Cv, is that what you said? That's the right answer, even if you didn't say it. But so the other one is, this is for constant pressure. So this is the slope of constant pressure, when the constant pressure process, and dt by ds equal to T over Cv is the slope for or of constant volume process. Can you also again use Gibbs equation for getting the constant volume slope? I'm sure you can do that, but this is something which is readily available on the board. Can you see it? Can you replace TdS equal to dH minus dP by rho? I'm doing it because I wanted you guys to be fluent with this. It's du, which is internal energy, plus d of PV or P by rho minus dP by rho, right? And you can easily manipulate this to see that this is Cv times dt, internal energy, du, and this ideally should probably become P dV. dV is, V is 1 over rho. I'm sure some of you have memorized this also, it's not that difficult, but this is it. So constant volume, again you can easily see that the last term will drop out and you will get dt by ds as T over Cv. You just rearrange that small little equation there. Okay, so given a point, the constant volume slope has Cv in the denominator, and we have Cp over Cv equal to gamma, and gamma is greater than 1. So the slope of a constant volume would be higher. It has Cv in the denominator, which is a smaller number. Can you see it? If I extend this idea a little further, can I say that okay, let's look at these two lines. There are two constant volume lines. Will they be parallel? Will they be converging, or would they be diverging, starting from left to right? So that has an implication on your work output. The vertical lines are work output, input and output. So I'm sure you would want the right side vertical line to be longer, so you get more work output than the left one. But can you see it happening from these equations? So mathematics and physics has to come together, right? It should make sense, and it should be easily derivable from the mathematical equations. Then that is really a logical and a rigorous way of doing things. You can see it. Will they be parallel, diverging, and that's because T is smaller. So what we are saying is, if you take two constant volume lines, if you go to a higher T, the slope will be higher, because the slope is T over Cv. Cv is constant for the entire full domain. Everywhere Cv is constant. The gas is ideal perfect gas. The same thing is true for pressure lines. Two constant pressure lines will also diverge. Okay. So in fact, the constant pressure lines become more important for our aircraft engines, but our argument is pretty much the same. So okay, with this a small little digression, let me come back to where we started to compare. If for a time being we leave out whatever is in the yellow box, we come back to put all the 3 and 4 cycles on the same diagram and see how they compare. So 1, 2, 3, 4 is the standard Otto cycle, 1 to, well, let's put 3 prime to 4 and back to 1 is the diesel cycle. The Brayton cycle has two constant pressure processes. Heat addition and heat rejection both are constant pressure. So here is the other constant pressure which will be lower than the corresponding constant volume. Let's put it this way. Let's use a different color so that we can see things a little bit more clearly. Once again, if the drawing is good, then the two constant pressure lines should not be parallel, they should diverge. P equal to constant. And if we go back to the saying that the area under these lines will be equal to the heat transfer. If you integrate the area under each of these 1 to 4 or 1 to, let's call it 4, whatever, double prime or 4 prime, doesn't matter. Area under each of these curves would be the heat rejected in each process. So you can easily now see that the heat rejected in the Brayton cycle, so this is the blue one. Let's write this down, 1, 2, 3 prime, 4 prime. Diesel cycle is 1, 2, 3 prime, 4, and the original one, Otto cycle, is 1, 2, 3, 4. Standard. So heat rejection part, at least you can compare very easily here to say that both Otto and diesel cycles follow the white line. They will reject more heat than the Brayton cycle, which is at constant pressure. Rejecting more heat means less work output, right? And what's the minimum heat we can reject? That's the Carnot cycle. For the same T minimum, if I follow the same T minimum line, it has to be exactly horizontal. So that would be my minimum heat rejection. You can it's almost obvious on the graph once we make this connection of the area under those curves and make the and understand which curve lies above and below the which one based on the slopes. Then you can see that the Carnot cycle will reject the minimum amount of heat among all of those 4 cycles. Yeah? Should we draw 2 to? Well, okay. What I've said is I've kept the compression the same for all of them. Yes, and we had seen that it may not be the best way to compare 2 cycles. So I'm not. In fact, I'm going to that side. If you see, I'm only talking about this part. When you start comparing this side, then you have to worry about other things. Whether this line will be starting from 2 or at a higher pressure ratio, which diesel cycle allows you to achieve. Right, so that can be brought into this discussion if you want to, but with in terms of area under the curve and heat rejected, and you can kind of easily see the connection between the 4 cycles. In fact, the heat rejection part is easier to understand why a Carnot cycle is more efficient than all of these. But if you go to the heat addition part, we will draw a Carnot cycle of this kind. And that would be the heat addition. Again, that would beat all other processes in terms of the amount of heat added. So, if you're thinking that why should a Carnot cycle be at that point, why would it be this way? It's kind of obvious on the diagram, but physically, if you think about it, you want to transfer heat. We have replaced the combustion process with a heat addition. Okay, so we want a source which can transfer heat to the gas, to the working fluid. Now, if you want to transfer heat to the gas along this entire process, the temperature of the source better be higher than this, the highest point. Otherwise, there will be no heat transfer. The process will not be valid. So, if you are taking an external source and putting heat, doing a heat transfer, equal amount of heat transfer as what was released in combustion. Okay, there is no combustion in the standard process. It's all perfect gas and no reactions in this. We are just saying replacing combustion by equal amount of heat addition. So the heat addition from a source, the source has to be higher than this temperature. Otherwise, how would be? Now it better be at the minimum it can have is T max. And once you have a source at T max, then a Carnot cycle will get heat from the source at T max. That's the way we have defined it. That's the way Carnot defined it. It may not be possible to do realistically, but if you do it, obviously we'll get the best and get the most heat out of it. Questions? Okay. In fact, there may be many other ways of comparing this, as the question came up, that whether this, when we have a Brayton cycle defined for some T max, you may not want the heat addition to stop here. You may want it to go all the way to T max and then come down. So there may be many variations of this, this cycle. But this is an easy way of seeing why one is better than the other in terms of efficiency and what is the best we can achieve. Okay, so I'll leave the details to you guys and see if maybe some form of this may end up in the question paper, just to juggle our understanding. The next thing I want to take up is two important ideas. Important because they are very helpful and useful in aircraft engine analysis. Total pressure and total temperature. What we had seen earlier was probably total enthalpy, right? When we did first law applied to flow process, we came up with total enthalpy. We'll see how that comes up. That's also related to this. In fact, let's put it down anyways. Total enthalpy. In fact, let's start with first law, where we say m dot ht, well, out minus ht in equal to q dot minus w dot external. We all kind of remember at least some form of this equation. We have a flow through device which can be the entire engine, which can be part of the engine, which is, let's say, combustor or a compressor or a turbine, whatever it is, or for that matter a nozzle or a intake duct. This equation says mass flow rate times the change in total enthalpy across from inlet to outlet of that, and now for the time being we are assuming only one inlet, one outlet. Works out fairly well for most of the aircraft engine analysis. The change in total enthalpy is because of heat transfer and because of external work. External work is most of the time shaft work. As we saw in the midsum paper, even if there is friction, does not come into the picture. And external work is anything which is not flow work. That's another way of thinking about it. Anything which is not flow work has been dumped into external work, and the flow work has been taken out of work interaction and dumped into enthalpy, right? So we have easy way of kind of putting things together. This is a representation. This is a way to quantify the total amount of energy. So its total amount of energy change of the fluid can be either by adding heat or taking away heat, or by doing work by external forces, not the flow work, which is the pressure which is inherent to the fluid. That is not external work. Okay. So with this, so we have seen total enthalpy here. I'm going to come back to this equation after a while, after we do these two things, understand total pressure, total temperature, and come back and see how they relate. And we'll finally end up again on a TS diagram, because that is where everything fits in when you look at engines. All right, so let's go back to aerodynamics. You have seen this before many times in A152, and you've probably seen this more in your fluid mechanics. You'll see more of this also in your aerodynamics course. The streamlines look something like this. And we are aware of this point, which is called stagnation point. Excellent. And the pressure that we measure at the stagnation point is called the stagnation pressure. What's the temperature that we measure at the stagnation point called? That's a little more tricky, but I don't think it came up in A152. Neither did it come up in your fluid mechanics course, because we are blissfully we throw away all the changes in temperature, saying it's incompressible. Nothing changes, and we don't want to heat the gas or anything in your aerodynamics. It's a very nice simple flow over an airfoil. It's also, the temperature is also called stagnation temperature. Okay, and it turns out the stagnation pressure is same as total pressure, and stagnation temperature is same as total temperature. Okay, so now let's do a few simple things to see how it works. Let me do one more thing. If you're measuring the temperature at anywhere else, the pressure measured at not the stagnation point or anywhere else is called the static pressure. And why is it called static pressure? Stagnation we know, because the flow kind of stagnates. But why is the other one called static pressure? The flow is not static. Say again? Static and dynamic. Dynamic, okay, saying static and dynamic. I don't know if that's the way to think about it. Say again? Dynamic pressure okay. Okay, so fine, something of that sort. I would put it this way. Static pressure is the pressure you would measure if you are sitting on the flow and flowing with it. There's no flow if you're sitting on the fluid element. It's just a pressure, and that's a static pressure. You're static with respect to the flow, or with respect to the fluid element which is going along the streamline. Same thing would happen if you put a probe, as you just said. If you had made a small hole here and put a probe, you would measure the static pressure. If you put something which is perpendicular to the flow, if you had put in a probe like this with a hole in the front, again it will stop the flow. That will again stagnate the flow, and it will get stagnation pressure. But this one is static pressure. So let's write that here. And the same thing applies to static temperature. T and P, and stagnation pressure and stagnation temperature, generally we use it P naught or PT. Let me put T for total. Because in propulsion, in our engine applications, we'll call it total temperature and total pressure more often than stagnation temperature. The terminology is slightly different, but the idea is same. Okay, so let's go back to Bernoulli's equation. Just for once, I have told you repeatedly not to use it, but I'm going to break that law and say P plus half rho V square equal to constant. And then we said that at the stagnation point, velocity is 0, so we put this as P naught many times, but let's put PT. The equivalent, and then before going to the next one, what are the assumptions for this? Isentropic, really? You're probably right, but I think, incompressible, inviscid, and many, many more things. But let's write the two most important things. Inviscid, in fact, that is the most important thing, and incompressible. Inviscid is the most important thing for our purpose, what I'm going to say next. So when it is compressible, you cannot use this. Just put a big, do not use Bernoulli's equation. But what's the equivalent thing you can use? H plus half rho v squared. You're absolutely right. No, not quite right. H plus half rho v squared, let's write it. And then see if we got it right or not. Have H plus half rho v squared constant? Half v squared, very good. Self-correction is the best. Where did you get that from? Yeah? Of course, that's equal to total enthalpy. Energy equation, something like that. Anybody else? From where did you get it? Exactly, that's the best. It's right there on the top. We got it from that equation. If you can see the connection, you know, that is the basic equation. It applies every time. You can do it. It's the most general form. You can apply it anywhere. All we're doing is we're applying this to this streamline, starting from a point here to the stagnation point. Okay, and on this streamline, there is no external work, or let's say there is no heat transfer. We are not adding any heat. No, not burning any fuel or nothing like that we're doing. So Q dot is 0, negligible, let's say. There can be some heat transfer across, but it's not much. External work can be from shaft work, no shaft. And it can also be because of friction, if you go back to the midsem problem, and probably you have to convince yourself that friction is very small, or we can say that it's inviscid. The effect of friction is very small along the streamline. Effect of friction only comes up very close to the wall in a boundary layer. We are out of boundary layers. So no really big concern of friction. So once we apply that, these two drop out. All we are saying is HT out equal to HT in. Out and in are the 2 end points of the streamline, whatever we have considered. It's no flow through device anymore. Or you can place a flow through device if you want to, but doesn't matter. It's applicable to a flow streamline also. So that is your equation. So here it is. I'm going to now quickly put this by saying I'm going to equate this H plus half V square, which can be at any point, or let's say the first point, beginning of this streamline where we have placed the first marker, and at the stagnation point, velocity is 0, HT. Fine, this much we understand. That's a total enthalpy. And then we say everything is a perfect gas. So we quickly modify this to temperature. And what do we have? We get this equation. If you have already seen this, Tt equal to T times, anybody has seen this equation? It's a very popular equation. Not yet probably. Exactly. Maybe you have seen it. Total temperature is static temperature times 1 plus gamma minus 1 by 2 m square, Mach number square. Given the Mach number, given a flow at any point, well, let's say first this. If we have, at this point we have T and m, which is, m is Mach number, which is velocity divided by speed of sound. Speed of sound, let me put that for record, m equal to velocity v, which velocity I put to the cross v, the cross on the v, divided by speed of sound, which is gamma RT. So if you know the velocity and temperature, then you can calculate Mach number. Once you have that, you can calculate the total temperature, which is nothing but the stagnation temperature. So now I'm going to say that total temperature is equivalent, not equal, to total enthalpy. Fine, the two things are related by Cp. Total enthalpy, we just said, is a measure of the total amount of energy in the flow, not the fluid, the flow, because the pressure work comes in. So total temperature is also a measure of the total energy. Let's write it a little bit more clearly, because this is one of the most crucial concepts which I like to emphasize. It's a measure of total energy in the flow. Okay, so we'll leave it at this and come back to it in a few minutes if you have time. Let's go back to total pressure. So if we cannot use Bernoulli's equation in a compressible flow, how would we get total pressure now? You only know this, and now let's say we also know pressure at this point. Yeah? I probably know the answer. You guys know the answer, yes? Louder? Louder, louder. You probably have P and T relation for ideal gas? For adiabatic? Adiabatic process. So we just said that there is no heat transfer, and in fact, there is no heat transfer, there is no viscous forces, it's actually an isentropic process. So, P, well, T is proportional to P to the power of, is that gamma minus 1 by gamma? Just check it, please. Just exponent, I'll put a question mark, I tend to forget. So, T total divided by T is equal to P total divided by P to the power of gamma minus 1 by gamma. 1 minus gamma minus ulta, opposite of that, yeah? Please check it and correct it. Just please correct it in the notes. Huh? I think let's move on a little bit faster because I need to get to where I want. So P total equal to P static times that factor here, 1 plus gamma minus 1 by 2 m squared to the power of whatever that other power that comes up in terms of gamma. Okay, fine. So just fill it up. Good. Now comes the next step, crucial step. I'm going to draw TS diagram. Make space here, sorry, to erase quickly. But here is my TS diagram. We have 10 more minutes, right? Yeah. This is a little crucial step where I have TS, TS, or yeah, let's start with TS. Here is my first point. Let's do this. That's the starting of the streamline where I placed my first point. And where do I have the stagnation point relative to this guy is my question. On the TS diagram. We know where the stagnation point is on the airfoil. But now I'm saying on TS diagram because that's what's going to make a hell of a difference to us. Parallel to T axis and go vertically up. Correct. That's what the only crucial thing I want to see. So here is my stagnation point. So this is T. This is total temperature. And through every point I can draw a constant pressure line. So here is my constant pressure line for the value of static pressure, whatever the free stream pressure was. Was it atmospheric pressure? Fine, you can take the value of atmospheric pressure, draw the constant pressure line. And here is the other, this line corresponds to another constant pressure, but the value is total pressure. Okay. Now we'll make a change on this plot, for which you may need to make a new plot, but I have the luxury of or constraint of time and space. I'm going to convert this axis to H, enthalpy. So you are essentially scaling the y-axis by a factor of Cp. That's it. and here I am going to call it H, and the other one is HT. Fine. We know all the symbols that are coming up on the plot. What is this vertical height equal to? Half V square, very easy. So this is an easy one. V square by 2. So for every point in the flow, wherever it is, you can plot the value of temperature and entropy, or enthalpy and entropy. You will get a point on HS diagram. For every point on HS diagram, there is, if you add V square by 2, you will get another point, which is the total enthalpy or the stagnation point corresponding to the point in the flow. So what I am saying is, take any point wherever you want. Take any point on a streamline, off a streamline, any point you take, you can get you can measure temperature, pressure and Mach number or velocity at that point. Once you have these three quantities at any point, you can place a point for the values of static, temperature, pressure and entropy, and you can locate the corresponding stagnation values or total values. The flow doesn't have to come to a stagnation point. The flow along this streamline will never come to a stagnation point. It is going below the thing. Doesn't matter. But there's always some kind of a equivalent point which represents the total amount of energy in the flow. So what I'm going to say is, if I can make a little more space here, which I'm going to say that the two quantities I've written down here and clear out a bit more of this, we don't need that anymore. These two quantities, I tend to call them as they're a concept. The flow may never really come to a stagnation point, but we don't need the flow to come to a stagnation point to get its stagnation pressure and stagnation temperature. These are ideas which represent the total amount of energy in the flow. You don't have to bring it to rest to get that energy. You don't need to measure it. You know the velocity and you know the temperature, you can get its value. But that value, that total temperature is really important. As soon as we go on to the TS diagram and we represent all our engine functioning on a TS diagram, what matters to us is total enthalpy. In fact, the top equation there tells you why it matters so much. Because what we are interested in is work output from an engine. The last term in that equation. So all the work output is directly connected to the total enthalpy of the flow. What about total pressure? I didn't say that. Total pressure, if you do an equivalent thing, represents the total amount of momentum in the flow. And why is momentum important? We are all dealing with energy in thermodynamics. Drag, a little bit more. Yeah? Thrust. That is because of the change in momentum. So we have to keep track of the total pressure also. You don't want to lose much of it. If you lose a lot of total pressure, your thrust will be affected then. So we have 4 more minutes. I'm going to do one quick thing, go back to Gibbs equation and do a little juggling around to show you how total pressure is so damn important. Okay, so let's come to, I think we don't need this for the time being. T ds equal to dH minus dP by rho. This is the starting point. This is our basic Gibbs equation. Let me write that down. Gibbs for perfect gas, we have delta S equal to Cp ln T2 by T1 minus R ln P2 by P1. Okay, now I want to bring out one more effect. So I'm going to say that if on the TS diagram, maybe draw it here. If I have a adiabatic process with friction losses. If we have an adiabatic process without friction, then it is isentropic, the straight line. But now I'm saying, if you still have adiabatic, no heat transfer, but if you have friction, how would you represent that on a TS diagram? And that comes very, very often handy the way we in our engine analysis. So, anybody can quickly think about that? So let me draw a few representative lines here. I need a bit more space, but we'll try to do it here. We start with a point, let's say between point 1 and point 2. 1 is the entry to this process and 2 is the exit. So here is my 1. Corresponding to 1, I have the stagnation point. In fact, many times we use the notation once T for total. So static values are at 1 are placed here, total temperature, total pressure are placed here. So let me complete the picture by saying this is P1, this is PT1, let's say. Right, exactly what I did there. But I'm doing it for the starting. So we have a process, let's say it's a nozzle, well, or a diffuser, entry of an engine before we come to the compressor. So here is 1, here is 2. No heat transfer, but there is friction on the walls. Okay. Well, friction on the walls. Let's say there's friction in general, so there's some losses. I'm going to draw is adiabatic and no external work. So total enthalpy will remain constant, total temperature will remain constant. So I'm going to draw this line, which represents T1T equal to T2T, and then I would come down to a point where we have P2 and this is PT2. I'm already going over the time, but does this make sense? If not, then we'll have to probably take it up next time. I don't want to really overshoot too much. This is the stagnation, this is the state 2 and this is 2T. I have drawn 4 points on TS diagram. 2 of them are the actual values of pressure, temperature and entropy at the entry and exit, and the other 2 are the corresponding total temperature, total pressure points, which again the flow does not come to stagnation, but the corresponding stagnation points, stagnation values are plotted in TS diagram. I have connected the two total temperatures by same horizontal line because they are same with no heat transfer and no external work. Total enthalpy is conserved and total pressure changes. So I want to come to the total pressure and see how do we quantify the total change in total pressure, total change in stagnation pressure, and how it relates to the process. That is the connection we are getting to. But I think we'll have to stop here. We are already going over time. Next time we'll pick it up from here.